Hi, welcome back. This is Professor Ridge and today's lesson on section 4.4, inequalities in two variables. Okay, so determine whether each ordered pair is a solution of the given inequality. This is number 7 in the exercise set. So if we have a point 2, 3, is that a solution to 2x minus y is greater than negative 4? Now, if you recall, a solution means that if it's a replacement for the variable, or in this case for the variables, then when you plug them in, it gives you a true statement. So we're asking, is this a true statement, yes or no? Question mark. So we got negative 4 minus 3, that's negative 7. Is negative 7 greater than negative 4? The answer is no. So negative 2, 3 is not a solution. Let's try another one. 1, negative 6, and 3x plus y is greater than or equal to negative 3. So we're going to put in 1 for x, negative 6 for y. And is that a true statement? So 3 minus 6, negative 3 greater than or equal to negative 3. And the answer is yes. Right, because they're equal to. So or statement. Alright, so this actually would have a bunch of solutions, not just one. So again, if we want to solve it, instead of saying solve it, we say graph, because a graph is a picture of the solution set. So we want to be able to look at a graph to see what's true and what's not true. Okay, so before we do 2 dimensions, I want to consider 1 dimension, 1 variable. So if I ask you to graph x equals 2 on a number line, 1 dimension, all you would do is you'd figure out where 2 was and put a dot, a single point, right? X equals 2 is that single point. If I asked you to graph x is less than 2, you would find where 2 is. I always ask this question, why do you care about, what is significant about 2? Why are you putting an open circle there? And the point is, that's where it's equal to 2, and that splits the number line into 2 pieces. And the piece that's less than 2 is the one on the left, and that's what makes this a true statement. So first, before you can split the number line in 2 pieces, you've got to figure out, well, where's the point where it's equal to? Equal to 2. Same thing for here. So we go to the point where it's equal to 2, put a solid dot, because equal is part of the solution. And then that splits the number line into 2 pieces, and then we shade the right piece, which makes it a true statement. Those are the numbers that will be greater than 2. So the shading portion is the greater than or less than. That's half of the line, basically. The equal to is the point. Alright, so now when we go to 2 dimensions, okay, so let's look at 2 dimensions now. So if I ask you to graph y equals 2x plus 1, and if you recall, that would be a line. If we use slope-intercept form, we're going to start at y equals 1 on the y-axis, 0, 1. Slope is 2, which we write 2 over 1, up to the right, up 2 to the right 1. You do it again. Or I can go down 2 to the left 1. Draw the line through it. Now, the analogy I want to draw is between this 2 dimensions and 1 dimension, right? So in 2 dimensions, one equation is a line. In 1 dimension, x equals 2, the solution to that is a point. Okay, so in 2 dimensions, it's a line. So the line is like the point in example A above in 1 dimension. Now, when we went to x is less than 2, we first identified where x equals 2, and we put an open circle there. And And remember, the point is like in one dimension is like our line in two dimensions. So where is y? Your first step is going to do y equals 2x plus 1, and that's going to be what the boundary line that splits the plane into two pieces. So we're going to graph the line y equals 2x plus 1 up 2 over 1, down 2 over 1. But instead of being a solid line, because there's no equal to in here, just like up here, x is less than 2, we put an open circle, not a solid dot like we did in C. That was a solid dot. So what do you think the analogous thing would be like an open circle for the line would be? And hopefully you're saying a dotted line, or I say dashed line. Okay, make dashes. So the dashed line, dotted line, that is saying, okay, here's the boundary that splits the plane, because now we're in two dimensions, into two pieces. One piece is going to be y is less than 2x plus 1. The other piece would be y is greater than 2x plus 1. And I want the piece that makes this true statement. So there's two ways we can do this. One, we can pick a test point. Okay, so our first step would be, graph the boundary line. Y equals 2x plus 1, which we just did. And it's dashed because there's no equal to, right? The line is equal to. Now our second step is you're going to pick a test point on one side. So in this case I'm going to pick 3, 2. Plug it into the equation and test it. Is it true or false? Is it a solution? And the answer is 2 is less than 7. True. And then the third step would be shade the true side, because that's the solution set, the shading. Okay, so this is true, so this is true, so everything on that side is true, so I'm going to shade the true side. Okay, now there's a shortcut. If it's in slope-intercept form, y is less than 2x plus 1, you just put your pin on the line and less than is going down. So I could see I would shade that way, so that would be a shortcut. Now the shortcut only works when it's in slope-intercept form. Alright, so for C, we're going to do the same line. Y is 2, y is 1. Remember, we're going to graph y equals 2x plus 1, so up 2 over 1. And this one's going to be a solid line because of the equal to is part of the solution, because it's greater than or equal to. Pick a test point, which we already did, 3, 2. Plug it in. 2 is greater than or equal to 2 is greater than or equal to 2 times 3 plus 1, question mark. 2 is greater than or equal to 7, no. Right, it's less than, that's why it was true on the other one, so in this case it's false. So if it's false, that means the other side's true, and you shade the true side. Now generally I pick 0, 0 as my test point, provided it's not on the line. I'm going to use 0, 0. That's a little easier to do. Okay, but you can pick any test point, or you can use the shortcut, right? If it's in slope-intercept form, put your pin on anywhere on the line, and greater than is going up. Greater than is going up. Up. So you can see you get that same answer. Alright, let's try another example. Two ways you can do this. You can put it in slope-intercept form. So you're going to add 3x. Me personally, since both 2 and 3 divide in 6, I would find the x and y intercept. For me, that's a little bit easier. Most of my students like to do everything slope-intercept form. As you work more in math and get a little more comfortable with different techniques, you would do the other way. But anyway, so we're going to, y-intercept is 3. So we can put a dot at 3 on the y-axis. Slope is up 3 to the right 2. Which is off my paper, somewhere there. So I'm going to go down 3 to the left 2. Down 3 to the left 2. And that's going to be a dotted line, or dashed. Okay, the line, again, I can't emphasize this enough. The line is 2y minus 3x equals 6. Pick a test point, 0, 0. So if I plug it into the original problem, 2 times 0 minus 3 times 0, is that greater than 6? The answer is 0 greater than 6. No, this side's false. So 0, 0 is on the false side, so I'm going to shade the other side, the true side. Again, I could have done the shortcut since I went ahead and put it in slope-intercept form. But it only takes a second anyway to do a test point. Okay, 26 says graph on a plane x is greater than or equal to 3. So that you don't think that you could just do it on a number line. They're explicit about doing it on a plane. And if you recall, x equals 3 is a vertical line that goes through the point 3 on the x-axis. It's a vertical line. It goes through 3 on the x-axis, so that's x equals 3. And you want to be greater than, x is greater than 3, so you could do a test point. If you put in 0, 0, well, you only have to put the 0 for x. So is 0 greater than or equal to 3, yes or no? So that's false. So then the true side's the other way. Okay, so there you go. The other way, right, if you just put your pin on the line, x equals 3, and you want the x coordinates to be greater than 3, so that's going to the right. That's the other way you can think of that. But if all else fails, plugging in test points should never steer you wrong. So if you're not sure, do a test point. Because remember, we're shading the solutions, things that make it a true statement. And I want to do number 30. Number 30. Oh, we'll do 32. Negative 2 is less than y is less than or equal to 1. Okay, this one, if you recall, being in between negative 2 is less than y is less than or equal to 1, that's equivalent to this statement. Y is greater than negative 2, and at the same time, the intersection, y is less than or equal to 1. And again, y equals 1 is a horizontal line. That's y equals 1. And you want to be less than that, so it's going down. Y is greater than negative 2. So y equals 2 is a horizontal line. Y equals negative 2. And you want to be greater than that. So that's going up. And remember, for an intersection, this is an and statement, it's where it would get shaded twice, so it's just all the stuff in between. So there's that in between idea again. Alright, so that's how you graph that one on a plane. Now let's move on to graphing systems. And basically it's the same idea, kind of like the one we just did there. You're going to graph each line and then you're going to shade the portion of the graph that would get shaded by both of them, by both inequalities. Okay, so first we're going to graph the lines y equals x and y equals negative x plus 4. So y equals x is just 0, 0, 1, 1, 2, 2, y equals x. And it's going to be a solid line because of the equal to. So there's y equals x. Now that's in slope-intercept form. So we want y is greater than x. So if you put your point on the line, you know you're going to be going up. Okay, so we're going to go that way for y is greater than x. So basically you can't see what it, it's just the whole upper half of that graph above that line, y equals x. Now we're going to do the other one, y equals negative x plus 4. So the y-intercept is 4, and the slope is negative 1 over positive 1. So down 1 to the right 1, down 1 to the right 1, down 1 right 1, down 1 right 1. Solid line because of the equal to. So that's y equals negative x plus 4. And again, if I put my pin on the line, on that line, it's less than, so it's going down. Now you see these two lines chop the plane up into 4 pieces. You see those 4 pieces? Now which of those 4 pieces would get hit by shading from both lines at the same time? And if you look, right, this is getting shaded from that line, that's getting shaded from that line. So portion 3 of the graph will get shaded twice. These are systems are intersections. You got to think of it that way. So it's what gets hit twice. So that's what I would shade. So it'd be that portion of the graph, that fourth of it. All right, let's try one more here. Okay, so just to save some writing here, I'm going to convert them all to slope-intercept form. So for the first line, I'm going to subtract the x, and then divide by negative 1, so that flips the inequality around. So I'm not going to show work here. So that'd be subtract x, divide by negative 1. So you'll get that. And so that line, we go to y equals negative 2. Slope is up 1 to the right 1. And it's going to be a solid line. So that's y equals x minus 2. And we're going to shade up. So I'm just going to put a couple little marks just to kind of remind me that I'm going that way. Now I do the next line. I'm going to subtract x and divide by 2. So that's going to get me negative 1/2 x plus 4. So the y-intercept is 4. Slope is down 1 to the right 2. Down 1 to the right 2. And that's going to be a solid line also. That's y equals 1/2 x plus 4. Oh, it's negative 1/2 x plus 4. And I am going, if I look again, the slope-intercept form is going up, so I'm going to shade this portion. So if it was just these two lines, you should be seeing, right, the solution would be this upper, would be this portion right here, where I put 1. Now y is 4, y equals 4 is just this horizontal line, and we want to go down. Y is less than 4 is going down, so the solution is just this triangle it gets hit by all three pieces. Okay, so you could do it with 3, 4, 5, 6 inequalities, and it would be the solution would be the piece that gets hit by all of them. The piece that gets shaded, if it's 6 of them, they would get shaded 6 times. In this case, there was 3 inequalities, so the piece that gets shaded by all 3 is the final solution. Okay, and then you wouldn't write anything else. It's just inside that triangle. Alright, so that concludes the lesson for 4.4. Go to My Math Lab, complete your exercises there, and I will see you next time.